Before we move on to examples that use the kinematics or Suvette equation, let's talk about acceleration or free fall. Now, all objects fall to the ground because of the gravitational pull of the Earth. The force of gravity acting on a mass pulling it down towards Earth is known as the weight. The weight W of an object of mass m can be defined as W equals to mg, where g is the free fall acceleration. In the previous level at IGCSE or SPM, you would have learned that g is equal to 10 meter per second squared. And this is the value that you would have always used for your calculations. But in A levels, you're not supposed to use this value anymore. Instead, you're supposed to use a more precise value of 9.81 meter per second squared. For any object that moves through the air, they will all experience the same gravitational acceleration of g equals to 9.81 meter per second squared downwards towards the ground, provided that air resistance is negligible and weight is the only force acting on the object. In such cases, the object is considered to be free-falling, since the only force acting is the weight. As free-falling objects always experience the same gravitational acceleration, they will always fall at the same rate under gravity, regardless of their mass, size, and shape. For example, a hammer and a feather will both fall down at the same rate if they are free-falling. You might be thinking that if there are two objects of different masses that are falling, the object with the higher mass ought to be falling faster, because a higher mass means a higher weight, and a higher weight in turn means a higher force pulling the object down. So it ought to be falling faster, it ought to have a higher acceleration, but this is not true. If the weight is the only force acting on the objects, then both objects would always experience the same acceleration of g, regardless of their mass, regardless of their weight. To better understand this, let us consider the examples on the left, where we have two objects of different masses, m1 and m2, that are falling down. The only forces acting on them are their respective weights, w1 and w2. There are no other forces acting, such as air resistance. Let us also consider that the respective acceleration is a1 and a2. We apply F net equals to ma for both cases. For the first case, we have F net 1 equals to m1a1. Since the weight here is the only force acting, it is also the resultant force. So we get W1 equals to m1a1. We also know that W is equals to mg. So we have m1g equals to m1a1. From here, we see that the masses will cancel each other off, giving us a1 equals to g. We apply the same analysis for the second case. We get F net 2 equals to m2a2. The resultant force here is again just the weight. So we get W2 equals to m2a2. And then lastly, m2g equals to m2a2. Again, the masses will cancel each other off, giving us a2 equals to g. At the end of it, we see that a1 is equal to a2 is equal to g. Both of the falling objects have the same acceleration of g, even though they have different mass and weights. This is only possible in the first place if the only force acting on them is just the weight. What if, in addition to the weight, there are some other forces acting on a falling object? Would its acceleration still be equal to g? Let's look at the example on the right. We have an object of mass m that is falling down. In addition to the weight, we now have air resistance opposing its motion. Let's assume that its acceleration downward is equals to a. We apply F net equals to ma onto the motion. The resultant force is W minus R equals to ma. And then we expand it further, we get mg minus R equals to ma. And then we make a the subject, we get mg minus R divided by m. From here, it is clear that A is not equal to G. So in conclusion, the moment you see that a falling object has some other force acting on it apart from the weight, its acceleration will never ever be equal to G. Acceleration will only ever be equal to G if the only force acting is the weight.